The sun, our closest star, a colossal ball of plasma that sits 93 million miles away. And yet, its influence reaches far beyond its radiant surface. It has been the heartbeat for all life on Earth for billions of years. From ancestral stories of the sun to the scientists that study its every detail.
The sun is important to study for multiple reasons. One of the biggest reasons is that it's the giver of life. Everything that we do on Earth, energy-wise, is somehow derived from the sun.
So there's organisms, plants, microorganisms that are able to capture the solar light and synthesize it into organic molecules that then become the food source of all the other organisms.
And visit the cutting-edge instrument that is more powerful than any other solar telescope in the world.
It does seem counterintuitive to have such a large telescope really act and behave like a microscope on the sun, but it really does do that.
We'll embark on a journey to uncover the mysteries of this brilliant star, exploring its immense power and intricate complexities, trying to understand its critical role in sustaining life. Kala is revered as the giver of light and warmth. It means the sun in Hawaiian. The sun's energy fueled the formation of Earth's atmosphere and oceans some 4.5 billion years ago, creating the conditions necessary for life to emerge. Through photosynthesis, which means to make from light, plants convert sunlight into chemical energy.
The organisms that first developed the capacity to capture the sun's light and convert it into organic matter through the process of photosynthesis transformed the atmosphere on Earth that made possible the life that we have on the planet today.
The oxygen created through this process gradually accumulated in Earth's atmosphere, leading to the development of more complex life forms. Solar radiation from the sun, combined with the Earth's primordial atmosphere, likely played a role in the formation of amino acids and other vital compounds. Without the sun's consistent energy, our world would remain a barren, frozen planet incapable of sustaining life.
All plants need sun, and the reason is that they are at the bottom of the food cycle. They are the ones who can have the ability to produce oxygen, and they have the ability to fix the carbon, which is CO2 in the environment, fix it and bring it into an organic form to make sugars and other proteins and amino acids and other things to build the life forms.
On a cosmic scale, its gravitational influence helped stabilize Earth's orbit, maintaining a habitable climate, which allowed life to not only begin, but to evolve into the diverse ecosystems we see today.
The ecosystem is in combination with how the Earth rotates and revolves around the sun in general. That creates seasons, that creates your yearly activities of weather patterns, and it creates your day and night cycles.
It also influences the biological rhythms that regulate the behaviors of countless species. From the migration of birds to the blooming of flowers, to even processes inside our own bodies.
sun is not just involved in the photosynthesis part, it's also involved the red and the blue light spectrum of the visible light that we are looking at. They're also involved in various perceptions of red light reception and the blue light reception in the plant, or rather in any living organism we have. And that red light and blue light receptors in our bodies that actually regulate the growth cycle, a lot of metabolism in us, how we sleep, how we wake up, and how we grow and develop. And so sun is important for driving the synthesis of those things.
The interaction between sunlight and receptors within our body helps regulate our daily life. Even just exposure to sunlight is essential for our overall health. Every bite of food we eat, every breath of fresh air we take, how we feel, how we sleep, all traces back to the sun's energy. While it nurtures our planet, the sun also harbors a much darker side. For all the power it holds to create life, it also wields the power to damage it. Its dynamic surface is a roiling sea of hot plasma, where intense magnetic fields bend and snap, erupt, releasing massive amounts of energy.
Coronal mass ejections and solar flares are two different types of solar eruptive phenomena. Generally, what's happening is that there is magnetic tension that's built up. And so coronal mass ejections are large eruptions, kind of like volcanoes of like billions of tons of material that just come bursting off the surface. For solar flares, we usually see them happen around sunspots or active regions, and the active regions have these really complicated magnetic fields. There's sort of a twisting that happens and turning, so all of this tension builds up and then you get this burst.
These surges of solar particles send waves of harmful ultraviolet radiation surging towards Earth.
The sun is putting out a lot of energy, and some of that energy is intercepted and bounced back off the top of our atmosphere. But UV radiation, those are wavelengths that are a little shorter and a little more intense than the visible light spectrum. In humans, exposure to those UV radiations causes sunburn and other skin conditions.
The damage from UV radiation can lead to impaired cellular functions, decreasing the overall efficiency of photosynthesis. This can be especially harmful to marine plants, algae, and phytoplankton. These tiny oceanic organisms play a crucial role in maintaining the balance in Earth's atmosphere.
Just like people, aquatic organisms can be damaged by UV radiation. Some organisms, like fish, avoid the near-surface water so they don't have to encounter that radiation. Other microorganisms, like the ones that are doing photosynthesis in aquatic ecosystems and creating energy and food, they can't always avoid that UV radiation near the surface, and that can damage the biomachinery that conducts photosynthesis.
The radiation can also reduce the plant's ability to absorb light.
That is in many ways very detrimental to the plants, not only to the plants in general, for any living organism that we are looking at it. So what happens is the UV light creates some chemical modifications in the DNA chain. As the new DNA is being synthesized, they don't allow a proper synthesis of the new DNA molecule, and it can create or trigger cell death.
The impacts from the sun's radiation can spread even further. During solar events like solar flares or coronal mass ejections, these impacts can be amplified.
Now we know that solar storms, for example, that happen on the sun, come and directly interact with our Earth's magnetosphere and have a sizable role on the planetary environment that's around Earth.
The bubbles that come, these coronal mass ejections, and the solar flares are basically these big clouds of electromagnetism, and they impact Earth's magnetic field, which is our force field. A lot of material tends to sort of flow around the Earth, kind of like water around a rock in a river. But when that magnetic field gets buffeted by these giant clouds that are many, many times the size of Earth when they hit us, it causes our magnetic field to wobble.
major geomagnetic storms can have damaging consequences, both on the ground and above.
It has very, very important impacts on how we live as a society, especially as an electronic society. The connection with sun is critical. And we're constantly at risk of losing life-sustaining type of infrastructure to the next solar storm.
By studying the sun's magnetic fields and understanding the mechanisms behind these eruptions, scientists aim to better predict these destructive events.
So that has multiple downstream effects. That can affect satellites, that can affect astronauts, it can affect cloud production. It has many, many roles. But unfortunately, that connection between sun and earth system is extremely complex. And it gets even more complex as you get closer to the sun.
This is a huge area of study.
Understanding the solar environment, that atmosphere, the background, what's happening there, and then when you have storms erupt is really important for monitoring these systems because these systems can be so disrupted. From a natural human curiosity perspective, the more you see, the more you want to see.
And seeing more of our star is exactly what scientists are just now beginning to achieve from a very special place. Haleakalā, a massive shield volcano on the island of Maui, holds deep cultural significance for the Hawaiian people. Known as the House of the Sun, it is the place in Hawaiian mythology where the demigod Maui lassoed the sun, slowing its great journey across the sky. Near the summit, at an elevation just over 10,000 feet, is the National Science Foundation's Daniel K. Inouye Solar Telescope. It is the largest and most powerful solar telescope in the world. Managed and operated by the NSF National Solar Observatory, its focus is to help us understand, measure, and quantify the sun's explosive behavior.
With the Inouye Solar Telescope, it really is a microscope in a laboratory. And that laboratory for us is the solar atmosphere. Only in the sun do we get to see the plasma interact in the way it does. And that tells us not only things about other stars, but it also tells us fundamental things about plasma physics.
The sun may look like this steady object in the sky that provides the energy for us. On the other hand, it's a very dynamic object. And it all goes back to or is driven by magnetic fields.
If solar scientists can more accurately measure these magnetic fields, it will lead to a better understanding of how the sun changes and transforms from day to day.
What we need to really understand the solar magnetic field, how it evolves and eventually erupts in these, call it explosive events, is to measure the magnetic field very accurately. And what we have to measure is the strength of the magnetic field and the direction in which it points.
And if we can understand that basic physics and what's going on, then we can help the forecasters. So what excites me is that I think we're measuring new quantities, we're measuring new things with this telescope that fundamentally shakes up the way we're able to study these buildups of magnetic energy. And with that, I think we're going to have a lot of breakthroughs that, it's not going to be helpful tomorrow, but a decade from now, 2 decades from now, it's going to lead to exactly the type of tools that we need to live the way we do on this planet.
Cooler regions on the sun, known as sunspots, are a prime example where the Inouye's precision measuring of magnetic fields can lead to breakthroughs.
Sunspots are part of magnetic complexes that actually produce solar activity, like solar flares and coronal mass ejections. They're not just a flat object. Getting a handle on what the sunspot's three-dimensional structure is can tell us something about when and why solar flares and coronal mass ejections are formed.
To reach the level of accuracy needed to create predictive models, the Inouye's suite of highly sensitive and highly unique instruments provide scientists the ability to observe the sun with never-before-seen clarity. But the journey of a sunbeam's light through the telescope, down to the instrument laboratory where those observations can be made, is a complicated and mind-blowing feat of design that requires the collective knowledge of countless researchers and engineers.
We actually open a 4-meter hole in the enclosure, and the enclosure points towards the sun.
And the light would come through the aperture to the telescope main mirror. It reflects back up to the secondary.
And then we focus that through a series of other mirrors.
It's now concentrated into a beam that is much smaller.
Down several floors below us into the Coude lab.
In that rotating Coude laboratory, we have 5 main instruments. And in order to get light to multiple instruments, we have beam splitters.
Some of the instruments take images. We take an image of a particular light and
We analyze the sunlight in different ways using those different instruments. Polar emitters and spectrographs give us more physical information about what is going on the sun.
Not only do we want to get really good images of the sun, we also want to understand the magnetic field properties. And so what polarimetry can provide is an ability to see the magnetic fields.
other instruments look at only a segment of the surface. And in that segment, we disperse the light into the wavelengths, the colors of the sun.
But in essence, they're all trying to measure with very high accuracy the solar magnetic field and understand how it evolves and eventually leads to these explosive events.
The unmatched power of the telescope comes from its 4-meter, or 13-foot, main mirror.
This mirror is not actually flat. It's slightly curved. It's what we call an off-axis parabola. With this really thin mirror that we have, but really large mirror, you're going to get distortions due to the weight of it and as it's moving on that giant platform.
The Inouye uses adaptive optics, where the mirrors are warped to counteract its weight, turbulence, and other disturbances from Earth's atmosphere. The main mirror is outfitted with 142 actuators that change the mirror's shape once per minute.
So the surface, across this mirror of 4-meter diameter has to be accurate to less than a thousandth of a hair and has to be kept to that accuracy during the day as we're following the sun.
So the actuators help keep the beam shape of the light going through the telescope. And what they do is they push and pull the mirror surface. So you have 118 on the back and then 24 on the sides.
The main source of turbulence, as you might imagine, is the extreme temperatures generated at the telescope's surface. During solar observation, an estimated 13 kilowatts of thermal energy is created, or enough to power an entire home.
Well, pointing a telescope of this size to the sun brings with it its challenges. One of those is the thermal control of the entire telescope system. Because as we point at the sun, the mirror reflects most of the energy, but it also absorbs about 10% of it. And the mirror surface heats up. Once it's hot, generates turbulence and distorts the solar image. So we cool the mirror from the backside by blowing cool air to keep that front surface at ambient temperature.
The Coude Instrument Laboratory is considered the heart of the telescope and is where discoveries begin. It has a special capability, unique to solar telescopes. The instrument platform spins during observation.
The way the telescope moves across the sky, that motion of the telescope results in the image actually rotating in the focal plane where your detector is. If you're trying to map a particular region or if you're trying to take a long integration, then that just blurs your image. Any kind of motion over the time it takes to measure what you're trying to measure is going to blur. It's going to make the resolution not as good. So the way we get around that is we rotate our instruments.
5 scientific instruments share the sunlight that beams down from the main mirror. Additional optics have coatings on them, or gratings. and perform a crucial function.
And so what the grating does is it takes the white light from the sun and disperses it basically into a rainbow of colors. And this allows us to spatially select different wavelengths, different colors, which can interchange and allow us to send different wavelengths to different instruments. So it really opens up and expands the scientific capabilities of the Inouye Solar Telescope instruments. And it gives the scientists an opportunity to really tailor what they want to see and observe.
And if the lab is the heart, the instruments are the telescope's vital organs.
The instrumentation that's at this telescope is all custom built for a custom purpose. They're one of a kind. Each one of the instruments is slightly different, and each one not only can look at different types of light, but maybe in different ways.
One of those instruments is the visible tunable filter that captures images in specific wavelengths of visible light, revealing fine details of solar structures. Another is the diffraction-limited near-infrared spectropolarimeter, designed to provide high-resolution data in regions of the sun like sunspots, where magnetic fields are strongest.
It takes a tiny postage stamp on the sun and it slices up the light and feeds it into a spectrograph. So you get both the 2D spatial information and the spectral information all at once.
The visible spectropolarimeter measures the polarization of light across the visible spectrum, allowing for detailed study of the sun's magnetic fields. To observe the sun's corona in the near-infrared range, scientists use the cryogenic near-infrared spectropolarimeter, ideal for studying its faint outer layers. The visible broadband imager captures high-resolution images of the sun's surface in the visible spectrum, capturing details less than 12.5 miles. The release of the VBI's first image in January 2020 was the highest resolution image ever taken of the solar surface, and had the science community marking a new era in solar physics.
Yeah, that was very special for all of us to be able to finally see this. And it's, it's one thing to be a part of the team that is there when the instrument's taking the image. It's another for all the processing, and then for our data center and scientists who help process and make sure that that image is up to science quality, as well as something that we can all share and enjoy with the world.
The intricate cell-like patterns in the plasma left viewers marveling at the never-before-seen details of our star. It bombarded social media, magazines, and news outlets around the world.
That moment when you get the first glimpse where everything came together. The first time you see what you set out to see with the telescope. I think the moment that I'll remember decades from now is not only the first time I saw the image itself, but when I saw the image on the front of the New York Times. That moment, it just solidified everything. It solidified that we're doing something special.
The image sparked an increased curiosity in solar phenomena, its importance to us as a species, and the need for further study and understanding of the sun's behavior. This critical but often overlooked aspect of our lives was now getting its own moment in the sun. Here, above the clouds, in the house of the sun, the NSF Daniel K. Inouye Solar Telescope will someday reveal the complexities of our closest star.
Every time I show a movie of the sun to somebody who's never seen them before, their minds just sort of seem to explode. I think people don't realize that the sun has so much going on.
So the future, I think, will bring a lot of new results, a lot of new things that we learn about the sun.
The telescope will open new frontiers in solar science, helping us to better understand our universe, standing as a symbol of human curiosity.
Science is something that, is for everybody to learn about our natural world. And keep it in mind that that's something that's legitimately something that our society does. We seek, we try to find answers. And at the end of the day, I think we're better for it as a society.